In this tutorial, you're going to learn how to land a spaceship on the moon using dueling double deep Q learning. You don't need any prior exposure to reinforcement learning. You don't need any prior exposure to deep Q learning or double deep Q learning. You just need to follow along. Let's get started. Before we begin, allow me to address my relatively long hiatus from YouTube. I was furiously working to finish up the course, Deep Q Learning from Paper to Code. That drops on Udemy in the near future. It is presently under review. Everything is done from my end. I'm just waiting for them to approve the course. Of course, when it does drop, I will leave a link in pretty much all of my videos, as well as making an announcement video here on the channel, so you won't really be able to miss it. If you want to see what you will learn in that course, you can take a look at my GitHub. I've already posted the code there. That is at github.com/philtabor/deepqlearning paper to code. I'll drop a link here in the description and pinned comment as well, so you can check it out now if you're interested. All that said, let's go ahead and get started. So our imports are going to be relatively light. We're going to need OS for file joining operations to handle model checkpointing, NumPy to handle NumPy operations like random action selection for epsilon greedy action selection, the torch base package to get access to the torch.tensor function, which we will use to cast NumPy arrays to PyTorch tensors, because PyTorch is quite particular about the type of data you pass it. In particular, it doesn't want NumPy arrays, it wants tensors of specific types. We'll cover that in a minute. Torch.nn gives you access to the neural network layers. In this case, we're going to be dealing with strictly linear layers. In the course, we'll be dealing with manipulating screen images from the Atari OpenAI Gym. But for now, we're dealing with the lunar lander environment, which is strictly linear layers. nn.functional will give you access to the activation functions. In this case, we'll be using ReLU. And finally, optim is our optimizer, in this case atom, a variation of stochastic gradient descent with momentum and adaptive learning rates. So the first thing we have to address is how will the agent store memory so that it can learn from them later. So the easiest and most clean way to do this is to create a class, a replay buffer class, that will store the memories as some type of data structure and facilitate sampling of those memories later on. So let's go ahead and do that. So the constructor for the replay buffer class should take a number of parameters: the max size, because the memory should not be unbounded, you don't want to eat up all the RAM in your computer, and the input shape from the environment, which would tell it the shape of the observations to expect from the OpenAI Gym, in this case the lunar lander, which is a list of 8 elements. And we want to save the appropriate member variables in our class. The way I construct the memory is that I use NumPy arrays where I pre-allocate all of the space. You can use a DQ, which is a Python object that is basically a linked list, and this has a functionality where it will append objects to the end of the list and delete them from the beginning of the list so that it always stays bounded. If you do that, though, the difficulty is that you have to dereference a list of lists. You have a DQ object, which will store the list of the memories, which are, states, actions, rewards, and new states, and done flags. And so you have to dereference 5 items from that, and that can get kind of confusing. That's why I use the separately named NumPy arrays. It's just the cleanest implementation from a perspective of teaching, not necessarily the best perspective in general. Now, this quantity mem counter is the index of the last stored memory. Since we're not using a DQ, we have to keep track of where we stored the last memory, and so we do that by the mem counter variable. The first memory we want is the state memory, and that is shape mem size by input shape. And that needs to be a float32 data type to deal with the peculiarities of PyTorch. This star input shape allows us to accommodate input variables of just about any shape. So it will unpack a list. In this case, our environment will have shape 8, a list of 8 elements. So that is how we handle that. Let's do the new state memory. You can probably hear my son downstairs having a hoot. Okay, so the new state memory is pretty much the same thing. It's, you know, in terms of the array, it's not the same thing, but it is in terms of shape and data type. The next thing we want is the action memory, and that gets shape mem size, and it should be an np.int64. Now, it is not particularly important that it is np.int64, except for the fact that PyTorch is quite peculiar about the data. So just know that. And the reward memory will be an numpy float 32. And the terminal memory will be the memory of the done flags from the environment. The reason we need to do this is that the future reward the agent expects to receive depends on whether or not the next state is terminal. So at the end of the episode, it reaches the terminal state, and the value of all states, all future states, that is, when you're in the terminal state, is identically 0, because there are no more rewards to come, so you get no future returns from the terminal state, and so it should be 0. That means that when you calculate the reward, the agent's expectation of the future reward, that is, the targets in the update rule for our deep neural network, you must take into account that whether or not the next state is terminal. If it is, you set the expected future reward to just the reward from this state. If it is not a terminal state, then you have to discount the potential future rewards that come after the current state. And we do that with a terminal memory that acts as a type of mask, which you will see shortly. Next, we need a function to store transitions. And that just takes all the appropriate variables from the environment. So the first thing we have to know is, what is the index of our first free memory? And that comes from taking the modulus of the memory counter with the memory size. And then we take the memories and store them in the indices in the appropriate arrays. Terminal memory. And finally, when you're done storing the memories, make sure to advance the memory counter. So the next thing we need to do is sample the buffer. So this comes into play when the agent is learning. When it is learning from its prior experiences, you want to be able to sample the buffer or the memory of memories, the collection of memories uniformly. You don't want to sample one segment of memory more likely than any other, so we have to facilitate that with a random choice function. And that takes a batch size as input. Now, there are other ways of doing this. You can prioritize certain experiences based on their potential for future learning, but that is a more advanced method of sampling and best left for future content. Now, if you have filled up the memory, then you are free to sample anything from memory 0 all the way up to mem size. If you have not filled up the memory, you don't want to sample the memory of zeros, right? You want to sample the memory of actual memories that correspond to real gameplay, and you do that by taking the minimum of either the mem counter or the mem size, not the max, the minimum. The next thing we have to do is get our batch of random memories, and this will sample uniformly. It will sample from the 0 to the max mem from here, and it will sample batch size number, so in this case 32 or 64, from this range, so 0 up to max mem minus 1. It'll give you 64 or 32, whatever your batch size integers is. And replace equals false tells the NumPy random choice that once it selects a memory, it cannot select it again. You don't want to oversample memories. you know, it can give somewhat of an issue. And then all you have to do is sample the arrays and return their respective quantities. And that is it for our sample memory. So now we have to deal with the Dueling DeepQ network itself. So this gets its own special class, and we will give it the appropriate name of Dueling DeepQ network. So let's go ahead and write that. So the constructor will take a learning rate, number of actions, a number of input DIMs, and a checkpoint directory, as well as a name. So the name is useful for model checkpointing, so that way we don't save QEval and QNext networks over each other. That would be kind of catastrophic and defeat the point of model checkpointing. So this is where the OS import comes in. What we want to do is save our checkpoint directory for later use in case we need it when extending the functionality of our class, and create a checkpoint file, which is just the root directory, whatever, or rather directory structure you want to save it in, plus the name of the network. Onto the actual DeepQ network. So we need a layer to handle the input of the observations from the environment, and then I'll transform those into 512 neurons. And then for the dueling portion of our network, we need a value and advantage stream. I go into more detail on this in the class, in the course, but the basic idea is that the value network tells the agent what is the value of its current state, and the advantage tells it the relative advantage of each action in its given state. And in the paper, they show you that the two streams end up focusing on different parts of the image. It's actually quite cool. The value stream focuses on one part of the image versus the action part of action stream. So it actually learns, the two streams learn what is important for their relative functionality. And so the value stream takes the 512 neurons as input and outputs a single value because the state is single valued, it's just a scalar quantity. And the advantage function takes those same 512 inputs and converts it into a value of a relative value of each action. Now when we construct the Q function, we may be tempted to just add these two together, but you can't actually do this. We'll have to come up with some other way of handling it when we get to the agent itself. More on that later. This reminds me, I forgot something, but the next thing we need is the optimizer. And in this case, that is what handles the stochastic gradient descent functionality. In this case, we'll use optim. What do we want to, we will use atom. What do we want to optimize? We want to optimize the parameters of our network. And where does that come from, you might ask? And that comes from something I forgot up here. All PyTorch classes must derive from the base nn.module class, and that gives you access to this self.parameters. And it will perform the gradient descent with learning rate LR. Sorry about that. The next thing we have to concern ourselves with is a loss function. And in this case, it'll be a mean squared error loss. We're going to take the mean squared error between our target values and the predicted values of our deep neural network, where we shift the predicted values towards those target values. Next thing we have to do is handle the device selection. So if you have a GPU, you certainly want to use it. If you have more than one GPU, you can say CUDA 1, or you can say CUDA 0. And if you don't have one available, it'll select the CPU by default. Finally, we want to send our entire network to that device. The reason this is important is because PyTorch differentiates between tensors that live on the CPU and tensors that live on the GPU. The latter is a CUDA tensor and the former is just a regular tensor. And so you cannot mix the two types. They have to be on the same device, and so you have to be very particular about where you send stuff. The next thing we have to concern ourselves with is the feedForward function. Once we have a state, what do we do with it? We send it through the network and get the value and advantage functions out the other side. And this takes a state as input, so this has to be turned into a tensor before we pass it in. The first thing we want to do is pass our state through the network and then activate it with a ReLU function. Then we want to take that flattened input and get the value and advantage functions out. Notice that the V and A, the value and advantage streams, both share a common input layer. This is the case even in the version with the Atari library, where you don't have a separate convolutional network to learn images for the value and advantage function. You simply have one convolutional network, in this case one linear layer, to learn the input features of the environment, and then two separate streams to learn their respective functionality. And then you just return the value and advantage functions. Next, we have a couple of bookkeeping functions to save and load checkpoints. It's always advisable to print something to the terminal to say, hey, I am saving a checkpoint. And what are we going to save? We're going to use the torch.save function to save the network's state dictionary, state_dict function, and you will save it in the checkpoint file. Of course, in PyTorch, if you're not familiar, everything in terms of the layers and parameters of the network are saved as a dictionary. Kind of a neat way of handling that functionality. And the inverse function is loading a checkpoint. Stupid autocomplete. So what we want to do then is load a state dictionary from a file. All right, that is it for the dueling deep Q network functionality. So now we have to concern ourselves with the agent. Now, if you're kind of scratching your head, and the reason I structure things this way, the reason is that an agent is not a deep Q network. This is kind of a finer point of software construction. So it's, if you're coming from a data science background, not a computer science background, this may be foreign language to you, but the basic idea is that one of the significant advances in computer science was object-oriented programming. It helps abstract away functionality into classes and objects and structures. And the basic idea is that you have an is a or has a relationship. In this case, an agent has a deep Q network, or dueling deep Q network as it were, that tells it the values of advantages and action functions. But an agent is not just the network. An agent is also the network plus the ability to learn from its experiences. It is also a memory. It has a memory. It has the capability to choose actions based on that memory, as well as to decrement its epsilon greedy action selection parameter, as well as it having a whole host of other parameters that are relevant to its operation. So it is an example of an has a relationship, hence why I structure things this way. So let's code the agent class. And so this will take a whole host of parameters. So the first parameter we're going to pass it is something called gamma. So gamma is the hyperparameter that tells the agent how much to discount future rewards. So what this means in practical terms is that the agent knows that future rewards are uncertain because there is some uncertainty around the way it selects actions due to not just its own estimates, but in some cases even the environment as well. Some environments are stochastic, meaning the action you choose is not necessarily the action you get. So there is some uncertainty around future rewards, and so it discounts them by some amount between 0 and 1. And there's a power law, so 0 or 1 to the kth power, where it's however many k moves in the future. In this case, we're going to use 0.99. So a value of 1 means it's completely far-sighted and values all rewards equally. A value of 0 means it's totally myopic, only values its current reward. Epsilon is the fraction of the time that it spends taking random actions. So it'll start out at 1 and gradually decay down to a minimum value. You never want to go down to 0 because the agent can never be quite sure that its model of the environment is correct, and therefore it must always spend some proportion of the time exploring to test its model against actual experimental data. The learning rate, of course, number of actions, input dimensions, a memory size, a batch size, an epsilon min of 0.01, an epsilon decrement factor of how quickly to reduce the epsilon over time, a replace of 1000. So what this means is how often is the agent going to replace the target network. So it has, let me scroll down for you, it has 2 networks, one of which tells it the value of the current state and one of which tells it the value of the next states. It's the current and evaluation network, or eval and next, whatever you want to call it. But the basic idea is that the agent only performs a learning update for one network and then periodically copies weights of that network over to the target network. And the replace is the interval at which that happens. And the final variable is the checkpoint directory. And I'll give it a default of temp/dueling ddqn. Now you must make sure to do a make dir on that directory beforehand, otherwise it will give you an error when you attempt to save to a directory that does not exist. Of course, we need a colon there, and so then we want to save our member variables. Don't hit the caps lock key. Let's see, epsilon decrement. Next thing we need to concern ourselves with is the action space. So this is a list of integers in the range 0 to n actions that facilitates random action selection. That relates to the point of epsilon greedy action selection with the epsilon hyperparameter. And doing it this way just saves you a little bit of trouble later on. Next, we need the agent's memory. And the dueling deep Q networks. So QEval will tell us the value of the current state. And we need an appropriate name. I like to use the environment as part of the name as well as the algorithm you're using. You can use whatever convention you want. I also include the name of the network, QEval in this case. So the other network, the QNext, is pretty much identical except in the name. So let's go ahead and just copy paste. This will tell us the value of the next actions. And the reason we want to know is for our update rule. And we'll get to that in a few minutes. The next thing we want to concern ourselves with is the way it chooses actions. So as stated, it will use epsilon greedy. So that means it calculates a random number. If that random number is less than epsilon, it takes a greedy action. If that random number is, if the random number is less than epsilon, it takes a random action. If the random number is greater than epsilon, it takes a greedy action, meaning it takes the best known action given its current state. And so it must take its observation of the environment as input. So if we're taking a greedy action, then what we want to do is convert our observation to a state tensor, a PyTorch tensor, send it to our device, feed it forward through our network, and get our advantage function out. We don't care about the value function because it's just a constant. It doesn't affect anything. And then we can use the advantage function to calculate the maximal action. And when you actually want to get the maximal action out, you have to take the .item dereference function. The reason being that this argmax function returns a PyTorch tensor, which the OpenAI gem will not accept as input for its step function. So you have to pass it a NumPy array that you get with the .item function. If we're not taking a maximal action, that means we're taking a random one. By taking a random choice from the action space. And regardless of how you select the action, you want to return it. Next, we have a function to handle the interface with the agent's memory, that is storing a transition. And I should have an underscore because that is a new state, and done flag. Next, we need a function to handle replacing the target network. And you want to make sure that it's timed to do so. You don't want to do it when you don't need to. And that learn step counter is just how many times the agent has executed the learning function. And what do we want to do? We want to load the state dictionary from the evaluation network onto the QNext network. The next thing we have to handle is how is the agent going to decrease its epsilon over time? How will it converge to a mostly greedy strategy? And you can see here I'm doing a purely linear decrease over time. I'm just subtracting off the epsilon decrement if it's greater than the minimum, otherwise just set it equal to the minimum. You can do really any type of decrement over time. You can do an exponential, logarithmic, 1 over square root, anything you want. Just linear is the simplest way to do it, so that's how I handle it. And I don't know to what extent it really matters because it spends the majority of its time in the greedy state, mostly greedy, and does the majority of its learning there anyway, so it doesn't really matter as far as I'm aware. Next, we need to handle the interface between the agent and its saving network functionality. And loading functionality. All right, so that is it for the bookkeeping functionality. Let's go ahead and scroll down a little bit. So the next thing we need to do is handle the learning functionality. This is the of course, the really heart of the problem, and so we want to pay the most attention to this. So this doesn't take any input because we're going to get everything we need from the memory. The first thing we have to address is, what do we do if the agent hasn't filled up enough memories to perform learning? So if we set batch size, the number of memories it wants to sample each learning step equal to 64, but it's only executed 10 steps of learning, or even one step for that matter, what do we want to do? Do we want to have it learn from that one step 64 times, or do we want to just wait until it fills up its batch size of memory, which is what I opt to do. So if we haven't filled up the batch size of memory, go ahead and return. In PyTorch, the first thing you want to do at the top of every learning function is zero the gradients on your optimizer. And for this problem, the first thing we want to do is figure out if we want to replace our target network, and if we do, to go ahead and do so. The next thing we have to handle is the sampling of memory, so let's do that. Sorry about that. So you may be wondering why I don't convert stuff to PyTorch tensors in the replay buffer class. And the reason is that I reuse that class for all of the frameworks, and so it should be framework independent. And so we want to take each of these NumPy arrays and convert them to PyTorch tensors and send them to their respective device. You notice I have this t.tensor. There is also a t.capital tensor, and that is a different function. It does the same functionality. However, you need to specify a data type, and the lowercase tensor will preserve the data type of the underlying NumPy array, which is the behavior we want. Or you can use capital tensor and just specify data type here. It's just, I do it this way because it results in a little bit cleaner code. And that is most certainly a typo. Rewards. Next, we have to handle a little bit of a contentious point here on this YouTube channel. So, by the way, if you are getting dimensionality errors in any of my code, then I would encourage you to open up a formal issue on GitHub, but do so in a way that allows me to track down the issue. So when I run the code on my local machine, it runs fine. When other people occasionally run it, a minority it seems, they get issues, and that tells me it's probably a configuration issue. So they're running some different version of NumPy, some different version of whatever set of packages, and so it's difficult for me to trace down what the issue is. So if you open up an issue, don't leave a comment, rather open up an issue on GitHub and specify what your configuration is. You know, what version of NumPy, what version of whatever particular framework we're running in the tutorial is. Specify anything that might be relevant, and also specify that whether or not you've added print statements in to let me know what the dimensionality is, because some things will run, like in TensorFlow, it will do a reduce functionality where even if you pass in the wrong dimensionality, something that is batch size by batch size instead of batch size by number of actions, it will still accept it, but it will give you the totally wrong answer. So it fails catastrophically, but in a way that is totally silent and the worst possible case. PyTorch is a little bit less forgiving on that. I think, I'm not entirely certain. I haven't tried to break the code recently, but as far as I remember, PyTorch is a little bit more particular, and so it may break a little bit more verbosely, and which is a good thing. But either way, make sure to put in print statements so that way that you can verify dimensionality, so that you are actually doing what you think you're doing. So to deal with this, just all a long-winded way of saying I need this line of code, and this line of code is, and all this is an array from 0 to batch size -1 that handles array indexing and slicing later on. If you don't have this, you get the wrong answer. So this is a kind of critical line, rather silly, but it is necessary. The next thing we have to do is pass the states and new states forward through our evaluation and next networks respectively. And then we have to handle the next question of what is the value of the future states as according to the Q-eval network. And all of this is explained in the paper on dueling dueling networks. More precisely, this particular line really comes from the paper on double deep Q learning, which we cover in the course, of course, in the class, of course. But the basic idea is you need all three of these quantities to perform the update rule. If you need clarification on what double deep Q learning is, you can check out a couple of my other videos on this channel on the topic. Just do a search for it in the search bar, and you'll be led to the non-deep versions of it, but that'll give you the basic idea. So the next thing we need to handle is how do we add together the networks. So the Q learning comes from Q, which is the state action value function. And what it tells you is the value of each action given you're in some state. And in this case, we have not a Q function, but a V and an S, a V and an A, a value and an advantage function. And the question is, how do we combine these two quantities in a way that gives us the Q function, and that makes sense? Now, you can't just add them together because you have a problem called identifiability, and so you have to add them together and then subtract off some quantity. You can subtract off a max quantity, but in the paper they tell you that they settled on the mean of the advantage stream. So let's go ahead and do all of that. Good grief. as.mean. And you want to take the mean across the action dimension and keep your dimensions. 3 parentheses. And here is where the bit of confusion around dimensionality comes in. So this array indexing is absolutely critical. You need to take the 0 through 31 or 0 through 63, whichever your batch size, 32 or 64 is, and you want the values of the actions the agent actually took. And that's by taking the actions dimension, or actions subarray. And we do the same thing or something similar for the Q next. I need underscores here. Otherwise it will break. And I have something wrong here. Now that I'm looking at it, this should be a minus sign. So what we're doing, is taking the advantage function and subtracting off its mean. Minus as underscore dot mean. Dim equal 1, keep dim equal true. And we don't need any funny indexing here because we want it for all actions. The next thing we want is the similar quantity for Q eval. And in fact, we can even do this to make things a little bit prettier. Copy, paste, and I will call this Q eval and add in eval there. And we need to stick that on a new line. Okay. The next thing we want to know for our update rule is what are the max actions of the next states according to the evaluation network. And we take those across the action dimension. As stated earlier in the video, the next thing we have to handle is the issue of how do we value rewards for which the next state is terminal, and we value them at identically 0. So we handle that by doing this. So in this case, dones will act as a mask. So everywhere done is true, everywhere where the next state is terminal will give you a 1, and it will set the index of the queue next at that particular state to 0. So it does not value future states for which they are terminal. Self.gamma times q next. And then we want to take the indices and max actions. So the quantity, the target value, is going to be q next for the maximal actions according to the evaluation network. Whew, we are almost done. So the next thing you have to handle is the calculation of the loss function. And then backpropagation. And stepping your optimizer. And incrementing your learn step counter. And decrementing epsilon. Alright, so that wraps up the functionality for our memory, network, and agent. Now we need a function to test everything, so let's do that. So imports for this are also kind of light. We need gym to handle our environment. We'll need numpy to handle averaging over the last 100 games so we can get an idea whether or not the agent is learning. Of course, we'll need our agent. And we need a function to plot the learning curve. And I call this different things in different directories. It's kind of a misstep on my part, so I will do a quick check before when we go to the terminal to make sure I have the right function name. All right, let's do our main loop. First thing we want to do is make our environment. Set the number of games. Now, when I ran this before, I stopped after 250. It takes a little bit of time just because I want to demonstrate learning. I don't necessarily care about getting a winning score, but we will run for 500 games this time. And let's instantiate our agent. Oh, sorry. The load checkpoint, it just tells us whether or not we were going to do model testing. We can load a saved model and then test it using just to see if it actually worked without learning. Let's instantiate our agent with a gamma of 0.99, starting epsilon of 1.0, learning rate of 5 by 10 to the minus 4. Input dims is 8 from our environment. We have 4 actions, memory size of 1,000,000, epsilon min of 0.01, batch size of 64, epsilon decrement of 1 by 10 to the minus 3, and a replace interval of every 100 moves. So if we're going to load a checkpoint, we should do so. Oh, of course I forgot my colon. Next, we need a number of variables for our running of our games. We'll need a file name for saving our file, our plot, sorry. And I like to put the relevant hyperparameters in the name, such as the environment, the algorithm, optimizer, learning rate, and replace interval. I don't put gamma because I almost always use 0.99, so it's kind of assumed. We also need an array for the scores. We also need an array for the scores the agent received and its epsilons over time. And that is for the learning plot. So we want to iterate over the number of games, setting the done flag to false, resetting our environment, and setting the score equal to 0 at the top of each game. So to play each game, we say while not done, action equals agent.choose action, observation, and take the action and get the new state, reward, done, and debug info back. Increment your score by the current reward. Store that transition. Which you cannot read. Let me scroll down. There we go. And put that there. And then you want to learn and set the old state equal to the new state. And you have to do this so that you are actually learning from the, so that you're actually choosing an action according to the current state of the environment. At the end of every episode, you want to append the scores and calculate the average score. And that's just for printing out to the terminal. And we'll use a print statement to let us know where we are. The score we received, the average score of the previous 100 games, the agent's epsilon. So I don't really need those spaces there. And that is it for our debug statement. Every 10 games or so we want to save our model. You can use whatever metric you want. You can say if the score is better than its best known score, then save. You can do it every 20 games, 50 games, whatever. I use 10. And you want to append the agent epsilon, the agent's epsilon to the epsilon history. And finally, at the end of all the games, we want to do our plotting. And this is just the x-axis for our plot. I believe it's plot learning curve. All right, so let's head to the terminal and see how many typos I made in the last 45 minutes. All right, here we are. Let's give it a try. Dueling DDQN lander, that looks right. Name SLF is not defined. Of course, it should be self. Let's correct that. And that is way back in line. What is that? Line 18. Let's come all the way back up in the other file, of course. Let's go all the way back up here. Self.memory size. Okay, it doesn't look like I did that elsewhere. Let's head back to the terminal and try it again. Once more. Okay, I have an unexpected argument in my initializer for the, looks like the agent class. All right, let's handle that. And so, of course, the error is something stupid as always. I forgot 2 underscores. Good grief. All right, so let's head back to the terminal and see how it does. Once more. Okay, so this is straightforward, so I know what happens here, so let's head back to the code. So what's happened here is I've forgotten my super constructor. and that is needed because I'm deriving from nn.module. All right, let's head back to the terminal and see what else I messed up. Once again. Of course, that's simple. So, of course, load checkpoint is a Boolean, not a function. All right, once more. And I misspelled observation. Typical, typical. That's in the main function in line 30. Observation. Observation. Alrighty. Let's try that again. Has no attribute learn step counter. Okay, that's simple. That's probably because I forgot to add it. Right there. All right, once more. And there we go, finally. And here I was hoping I'd make it through without any errors. Of course, that's too much to ask. So I'm going to let this run, and when it's done, I'll go ahead and wrap up the video. See you then.
All right, it has finished running, and you can see that on the terminal it indicates a final score of around 175 points, which is a little bit low. Earlier on it achieved a score of something like 194 points. So it's oscillating around a little bit. There are two potential reasons for this. So one reason could be that the learning rate was a little bit too high. The 5 by 10 to the minus 4 could be about a factor of 5 too high. We could retry this with 1 by 10 to the minus 4. The other possibility, if you take a look at the learning plot, is that the oscillations are usually due to too small of a replace interval. So instead of 100 games, 100 moves, we could do every 1,000 or so. That is another hyperparameter to play around with. I encourage you to do that. Do a git clone of this and play around with it and see what type of results you can get. I hope that was helpful. In the next series of videos, we're going to be looking at all kinds of different stuff. We'll probably move on from here to more policy gradient method stuff, as well as some more generalized machine and deep learning content. Make sure to subscribe so you don't miss that. Hit the notification bell, and I look forward to seeing you in the next video.